Welcome students. Today we are starting a new chapter in organic chemistry, which is very easy and quite interesting. The name of the chapter is coordination chemistry. Now, in the introduction of the coordination chemistry, if we give the introduction to coordination chemistry, what does coordination chemistry deal with? Coordination chemistry, I'll be using the symbolic form CC, coordination chemistry. It deals with study of coordination compounds. Coordination chemistry deals with study of coordination compounds. So in our chapter on coordination chemistry, we'll be studying different aspects of coordination compounds. One will be what actually these coordination compounds are, how these coordination compounds are different from the double salts, and the third will be the different modern terminologies that you use in coordination chemistry about coordination compound, the modern term. The term coordination compound is itself a modern term. The old term for coordination compounds is the complex compound. So they are quite complex. Then we have the different modern terminologies that you use in coordination chemistry, which you must be very familiar with, because the rest of the topics on coordination chemistry will be all based upon the understanding of the basic terms in coordination chemistry. Then after I give you the idea of the terms, we deal with coordination compounds in detail. Number one is how to write the structural formula of the coordination compounds. Then how to write the IUPAC name of the coordination compounds, very, very important part, where we'll be studying the different rules upon which the IUPAC nomenclature of coordination compounds is based. Then coordination compounds are quite large in number. You will come to know when I introduce you to the coordination compounds. There's a huge number of coordination compounds, and one basic reason for them is that they show isomerism. So we'll be studying structural and stereoisomerism in the coordination compounds. Now after we do the isomerism, then how the bonds are formed and what types of bonds are formed in coordination compounds. We have for that three theories in coordination compounds. One is the Werner's coordination theory, which is the oldest of the three theories. The second is the valence bond theory, which we have learned in the 11th class, valence bond theory and hybridization concept. There we have applied that theory and the hybridization concept to the covalent compounds. Here it will be extension of that valence bond theory to the coordination compounds. And the third, which is quite modern, and you have no idea about it, you have not read it in the lower classes, which is the crystal field theory. Because crystal field theory, as you learn, will deal with two very, very important properties of coordination compounds. One is, most of the coordination compounds you will learn, they have color. Some are blue in color, like compounds of copper are blue in color. Iron in different oxidation states, their coordination compounds have different colors. So crystal field theory provides us an explanation for the color of the coordination compounds. Then coordination compounds again show another important property called magnetic properties of the coordination compounds, and valence crystal field theory provides complete explanation about the paramagnetism, which is one of the magnetic properties, and diamagnetism of the coordination compounds. This is your our objective in this chapter of coordination chemistry. So I have introduced the term coordination chemistry. It deals with study of the coordination compounds. The old name for these coordination compounds, is the complex compounds. They are called complex compounds. And we have many, many complex or coordination compounds. Some are man-made and some are naturally occurring. The naturally occurring coordination compounds, three compounds are the one which have many biological uses in our body, in the body of in the plant body. They have so many uses. One of them is the hemoglobin. And you know what is the function of hemoglobin in the body. It acts as a carrier of oxygen. In your chapter on, in your biology, you must have read it. This hemoglobin is a coordination compound of iron, Fe. And you will learn with the passage of time that every coordination compound contains a metal. And in most of the cases, that metal is a transition metal, is a D block element. And iron, as you know, it belongs to D block of the periodic table. And it has a biological use. Number two, vitamin B12, which is again naturally occurring, vitamin B12. Also called as cobalamin. Cyanocobalamin. It is a coordination compound of cobalt. That's why it's called cobalamin, and it has uses. In our body, vitamins act as coenzymes. There are many biological processes which are catalyzed by enzymes, and the enzyme activity for those enzymes, these vitamins act as coenzymes. The third one, you have chlorophyll. The green pigment in plants, chlorophyll. It's again a coordination compound of magnesium. And magnesium is not a transition metal. As you know, it's an S block element belonging to group 2, that's alkaline earth metals. So all these naturally occurring coordination compounds have one feature in common, which is all of them contain a metal. And this metal you will come to know later on when we'll study the basic terminologies in coordination compounds. Where this metal is present, this metal forms the center of the coordination compound. Every coordination compound has a nucleus, and that nucleus is generally composed of a metal. It can be in the form of metal ion, a cation, or in some cases it's a neutral metal atom. But one common feature of every coordination compound is that they contain metals. So you can say the complex compounds of metals with different molecules or ions, they are the one which in modern terminology called as coordination compounds. Then there are some which are man-made, synthetic coordination compounds. There are man-made, the synthetic coordination compounds. And these synthetic coordination compounds also have many uses. And basically all those uses are generally in industries, they are in medicine, you use coordination compounds. One of them is, as an example, is the cisplatin. Cisplatin. In cisplatin, the metal which forms the nucleus is platinum. That's why the name platin. This is used in chemotherapy. For treatment of tumors. For treatment of tumors. But it is a man-made tumors. This is one of them. Then you have one more, which is called Turnbull's blue. Turnbull's blue. This is used as dye. Turnbull's blue. Again, it's a coordination compound which has a nucleus, and you will come to know later on, this Turnbull's nucleus is made up of iron. Iron is at the center. The third one is Prussian blue. Prussian blue. It's again used as dye. So similarly, there are many coordination compounds which are man-made, And all of them have uses either in industries, like these are used in textile industries for dyeing of textiles. Cisplatin finds use in the treatment of tumors and so on. So this is your intro to the coordination compounds. So one basic question here is, how do you define these coordination compounds? That for defining these coordination compounds, there is a type of coordination compounds. There's a type of compounds which are called as molecular compounds, also called as addition compounds. Molecular or addition compounds. These molecular or addition compounds, one of the types of molecular or addition compounds, there are two types. One of the types, they are called as coordination compounds. So coordination compounds are actually a type of general series of compounds which are called as molecular or addition compounds. The second type of molecular, also called as addition compounds, are the double salts. So a very simple one mark question can be asked, that differentiate between the coordination compounds and the double salts. What is the difference? Both of them are actually compounds called as molecular compounds. So first I will introduce you the term molecular compounds, how these molecular compounds are formed, and then you can easily say which of the addition compounds are coordination compounds and which are double salts. So here what I will do, I'll give examples of molecular compounds. Molecular compounds. And also you will come to learn from those examples how these molecular compounds are formed. If I take an aqueous solution of copper sulfate, which is, is a salt. Copper sulfate is a salt, and this copper sulfate is a blue colored salt. To this copper sulfate aqueous solution, if you will add liquid ammonia, aqueous ammonia, not liquid ammonia, aqueous ammonia. Aqueous ammonia means ammonia dissolved in water, which is also called ammonium hydroxide. So if you mix these two, both of them are stable. Ammonia aqueous solution is stable compound. Copper sulfate, it's aqueous solution also stable compound. If you add them, means if you mix them, how? In the ratio of 1:4, either by mass or by volume. So it means if you take 1 liter of copper sulfate, to that you will add 4 liters of ammonium hydroxide, which you call as aqueous ammonia. Or if you take 1 gram of copper sulfate, you will add 4 grams of ammonia. So they are mixed in a definite stoichiometric ratio. On mixing them, they are crystallized. When you crystallize them, that is on crystallization. Crystallization means you take this mixture and you heat it slowly up to a point called crystallization point. Then you stop heating and then cool the solution. On cooling, you will get crystals of the compound. That process is called as crystallization. So crystallization has two parts. One, you heat it, you boil the mixture up to crystallization point, and to recover the crystals, you have to cool the solution till you recover the crystals. So on crystallization of this solution, what you get a compound which is CuNH3 4SO4. You get its crystal solid. And you will come to know later on when we deal with this modern terminologies of coordination compounds and how to write the structural formula. You will know that there's a specific way of writing the certain compounds, that you put a metal and some molecules which are attached to it within the square brackets, and some ions are present outside it. This compound is a deep blue colored crystal, deep blue colored. It has a commercial name. This compound is called Schwitzer's reagent. is a synthetic one. I gave you so many examples of compounds. This compound is called as Schwitzer's reagent, and it has a use. What is its use? In industries, it is used for converting cellulose into silk. To convert cellulose into silk, cellulose is dissolved in this, and this Schwitzer's reagent acts there as a solvent. So it has an industrial use. So this is an addition compound. So what are addition compounds? From this example, it's quite clear. Addition compounds are the compounds which are formed by crystallization of a mixture of two stable compounds. Both of them can be salts or one of them can be salts. And they are mixed in a different ratio by volume, or they are mixed in a different ratio by mass. So the compounds which are formed by crystallization of a mixture of two stable compounds, both of them can be salts or one of them can be salts. On crystallization, the compound you get are called addition compounds. Another example is if we take an aqueous solution of potassium sulfate, which you know is a salt. To this, if you mix another salt solution, which is aluminium sulfate, aqueous solution of both, and then you crystallize this. When you crystallize this, on crystallization, how they are mixed? They are mixed in the ratio of 1 mole of this and 1 mole of this. It's always in a definite ratio. You take 1 mole of potassium sulfate dissolved in water, you take 1 mole of aluminium sulfate dissolved in water, and then you add them. That means you mix them. That mixture is then crystallized, as in the previous case. What you get? You get a compound K2SO4, Al2SO4, 3 times, and 24 molecules of water of crystallization. This is another example of addition compound. This compound is called as potash alum, commonly called as Fitkari. Fitkari uses an antiseptic, and it is used for sterilization of water, for killing the germs in water. You use a potash alum, the Fitkari. So both these are examples of molecular or addition compounds. And how they are formed? Again, on crystallization of a mixture of two stable solutions. Here both of them are salt solutions. Here only one of them is a salt solution. The compounds you get are called as addition compounds. Now these addition compounds, I told you, they are of 2 types. One of them, I have given you here 2 examples. Similarly, there can be many more examples which are formed in exactly the same way, that's by crystallization. One of the 2 examples, the first one, this is a coordination compound. Well as this potash alum, this is a double salt. I mean, certain things must be clear to you, even from the example, which are formed by crystallization of 2 stable salt solutions. The compound formed is a double salt. Now, what is the difference therefore between the double salt and the coordination compound? If you dissolve this double salt, say potash alum, in water, K2SO4, K2SO4, Al2SO4, 24 molecules of water. If you dissolve, say it's 1 mole in water, what will happen? It will lose its identity. That means it will no longer have this as its composition. Then what will happen to it? As every salt in solution dissociates into ions, this potash alum will also dissociate into ions. Now, which ions will be formed in solution? From the formula it becomes clear. One, if we take this as one molecule contains 2 potassium atoms which are present in ions. Therefore, 1 mole will contain 2 moles of potassium ions. So on dissolving water, it will break in to give 2 moles of sulfate ions. It will dissociate to give 2 moles of sulfate ions. Plus, 1 molecule of potassium sulfate contains 3 and 4 ions of sulfate, which means 1 mole will contain 4 moles of sulfate ions. Therefore, it will give you 4 moles of sulfate ions. One molecule contains 2 aluminium. Aluminium is present as Al3 positive. You know very well in salts, aluminium is present as a tripositive ion. Therefore, 1 mole of potassium will contain 2 moles of aluminium ions. So it will be twice Al3 plus aqueous. So what has happened to double salt? It's no longer the double salt. It has completely broken into ions when it is dissolved in water. So such molecular compounds, which have their composition, that means which are stable, as long as they are in the solid state. The moment they are dissolved in water, they completely break into ions. It means they lose their identity, they lose their nature. Such molecular compounds, which are stable in solid state, but in solution dissociate into ions, such addition compounds are called as double salt. Okay? So double salt, I think it's clear. I'll repeat it. This is one of the double salt which I have shown here. Double salts are addition compounds which are stable in solid state, in solid form. That means which have their composition, the formula, when they are in the solid state, but in solution completely break into ions. Such addition compounds are called as double salts. And one of the examples of double salt is potash 11. Here I have given you one more example of formation of an addition compound, which is Schütz's reagent, whose composition is that CuNH3 4 times and there is a sulfate. This is also an addition compound because it has again been formed by crystallization of 2 stable compounds. How come it is different from the double salts? It's in the solution. If you dissolve this compound, whose composition this, in water, that you prepare its aqueous solution, it will not completely break into ions. That's why they differ from the double salts. So what will be the composition? It will give you CuNH3 4 times 2 plus. This copper and ammonia will not break because they are present as a single entity. That's why this single entity is put within square brackets. And the one which are present outside the square brackets, they will be ionizable. Sulfate ion will dissociate. But it has not broken into copper ions. Suppose you have the solution of this and I ask you to test for the copper ions. On testing copper ions in this solution, you will find that the test will be negative. It appears that copper is not present there. If you test this aqueous solution for the presence of ammonia, you will again get negative test as if there is no ammonia. But we find from the formula that the compound contains, even in aqueous solution, copper as well as ammonia. Then why do we get negative test for individual copper and ammonia ions? Because copper and ammonia are not present as individual species. They are part of a single species. That species is present in the coordination compounds, while as that part is not present in the double salts. This part is the non-ionizable part. It's non-ionizable entity. Entity means part. This is where double salts differ from the compounds. This compound is a coordination compound. So what is a coordination compound? Coordination compound is an addition or molecular compound which is stable, which has its composition, which has its set of properties both in the solid state as well as in aqueous solution. Why they retain their properties in the aqueous solution? Because they contain in part an entity which doesn't break into ions. Since that part exists even in the aqueous solution, therefore coordination compounds are stable both in solid as well as in the form of the solution. So here we can give 1 point of difference between the two types of the addition compounds, that's coordination and the double salt. Both are addition compounds, but double salts are stable in solid state, but in solution completely ionized. Whereas coordination compounds are addition compounds. They are stable both in solid state as well as in the form of solution. Okay, so this is the basic difference between the two types of molecular compounds, which are called double salts and the coordinate. I have more examples of double salts. Okay, there are more examples of double salts. One is Fitkiri, double salts. One of them is, which is commercially called as Mohr salt. And what is the composition of this? Its composition is formula is it contains FeSO4, which is ferrous sulfate, ammonium sulfate, and since the hydrated salt, it contains 6 molecules of water of crystallization. So it must be formed by crystallization of an aqueous solution of ferrous sulfate and aqueous solution of ammonium sulfate. When you crystallize, you get a compound which contains both the salts, that's double salts. Now you can take this as a question, how many moles of ions are formed? How many moles of ions are formed when one mole of Mohr salt is dissolved, when 1 mole of Mohr salt is dissolved in water? Exactly on the basis of the potassium, where when 1 mole is dissolved in water, how many ions it will be forming, so you have to see the formula of the compound. It's a question for you. The second one, we can give one more example, it is carnallite. Carnallite is an ore of potassium, and in carnallite, potassium is present as a double salt. What is the composition? Potassium is present as potassium chloride, magnesium is present as magnesium chloride, and 6 molecules of water of crystallization. So this is its composition, and you can prepare it in the laboratory. How? You take magnesium chloride aqueous solution and potassium chloride aqueous in equal quantities, equimolar. Then you crystallize the solution. On crystallization, you will get the crystals of carnallite with this composition. Again, on the basis of the question which we did in double salt, you can yourself do this question, that when you dissolve 1 mole of carnallite in water, how many ions will be formed in aqueous solution. So these are their composition of their double salts only when they are present in the solid state. Now here there is one basic difference between a double salt and alum. What is that? All alums are double salts. All alums are double salts. But all double salts are not alums. Which means Mohr salt is a double salt, but it is not an alum. Potassium alum is an alum, it's also a double salt. So what property or what composition a double salt must have in order to be called as alums? For that, there's a general formula of alums. The general formula of alums is the general composition of alum is M2SO4 this metal in this sulfate must be having an oxidation state of +1, that means it must be monovalent, and M-2SO4 whole thrice. This metal, which have generally represented by M dash, must be having an oxidation state of +3, or if we use the old term for oxidation state, in one metal must be monovalent, the other metal must be trivalent with 24 molecules of water of crystallization. So if you look at Mohr salt, in this one metal is iron having +2 oxidation state. The other is ammonium ion, it has +1 charge on it. So it is a double sulfate, but it's not an alum. Why? Because though ammonium is monovalent, but the other metal is not trivalent, it's divalent. So this is not an alum, it's only a double salt. Whereas any double salt which satisfies this composition is called as an alum. Like if M is equal to potassium and M dash is equal to aluminium, you call it as potassium, K2SO4, Al2SO4 whole thrice. Potassium is monovalent and aluminium is trivalent. If M is equal to potassium and M dash is equal to chromium, then you call it as chromalum. What will be the formula? It will be K2SO4, Cr2SO4 whole thrice, 24 times water of crystallization. So, therefore, double salts, all double salts cannot be classified as alums. The double salts as well as alums are types of compounds which are called as molecular or addition compounds. So this was basically in the introduction part, that coordination compounds are naturally occurring, they can be synthetic. Now how do you define them? For that I gave you the idea of a general category of compounds which are called as addition compounds or molecular compounds, and one of the categories of those molecular or addition compounds are which you call as coordination compounds, and second one is double salt. So what we'll be doing ahead now will be taking up only the study of these coordination compounds, the type of addition compounds called coordination compounds. So our next topic will be the modern terminologies that you use in coordination compounds. Today I'll give you an idea of all those compounds, all those terminologies, and then we'll be taking each one of them individually, the modern terminologies, or modern terms. Terms used in coordination compounds. Those terms are, I'll take an example of a coordination compound and I'll label all the terms, modern terms in this coordination compound. This metal forms the nucleus of the coordination compound. So there's a terminology which is called central metal ion. This is at the center of the coordination compound, or it is also called as the nucleus. There you will find there will be coordination compounds which will have one nucleus, mononuclear coordination compounds. There will be coordination compounds which will be having two nuclei, binuclear coordination compounds, and similarly there will be polynuclear coordination. This is only one. The molecules which are attached with, which are ammonia, for these ammonia, we use a term which is called ligands. So in this coordination compound, ammonia are the ligands. This central metal has two properties. One is its oxidation number. I'll be abbreviating as ON. What is the oxidation number of metal ion, central metal ion, and how to calculate it. And second is called its coordination number. Coordination number. Cn, C dot n. So there are two numbers. One is the oxidation number, another is the coordination number. This coordination number is related to the ligands. Here, how many ammonia molecules are attached? 4. So we say the coordination number of copper in this compound is 4. This is its coordination number. Okay. Then there's an entity which I told is non-ionizable. What is that made up of? It's made up of copper and these 4, which you put within square brackets. This whole term put within square brackets, it is called coordination entity. It is called coordination entity. So from here it must be clear to you. Every coordination compound contains a coordination entity which is not present in double salts, and this coordination compound entity is non-ionizable. That's why they are stable even in the solution. And coordination entity is made up of metal ion and certain fixed number of molecules. Here they are ammonia molecules. That's called ligands. The part of the coordination compound which contains this coordination entity, which is symbolically shown by square brackets. This represents a sphere. Sphere means the part, which is called coordination sphere. So coordination sphere, which here is shown by square brackets, encloses the coordination entity. And the ions here, which is sulfate here, which are present outside this coordination entity, this is called as counter ion. This is the counter ion. So the details of these terms about coordination compounds will be continued in the next lecture. Thank you very much.